Hi, I'm Eun Pa from the Bureau of Meteorology. Here, I'd like to talk about our CMIP6 model evaluation work for the dynamical evolution of the Southern Hemisphere stratospheric polar vortex anomalies, which has been led by my Bureau colleague Ghislaine Bouchet and myself. In general, the Southern Hemisphere stratospheric westerly jet, which is also known as the Southern Hemisphere polar vortex, starts developing in autumn and peaks in winter in the middle latitudes at the stratopodes, which is at about 1 hectopascal level or 50 kilometers altitude. Then in spring, the Antarctic region becomes warmer and the stratospheric jet becomes weaker, and therefore it becomes more easily disturbed by large-scale waves propagating vertically from the low stratosphere and upper troposphere into the higher levels of the stratosphere, which further weakens and warms the vortex, causing it to contract towards the pole and move downward. This stratospheric polar vortex eventually breaks down in the upper to mid-stratosphere by mid-November to early December. So this is a general life cycle of the Southern Hemisphere vortex. When this seasonal evolution of the vortex happens faster than normal, we have anomalous polar vortex weakening and warming in our spring season. A typical dynamical evolution of anomalous springtime polar vortex weakening and warming often starts with a poleward shift of the winter stratospheric jet with increased westerlies on the pole side and decreased westerlies on the equatorward side of the stratospheric winter jet. These meridional dipole anomalies then move poleward and downward with time, resulting in the decrease of westerlies to dominate in the Southern Hemisphere extratropics in the upper to mid-stratosphere in springtime. These spring vortex anomalies then move further downward and promote an equatorward shift of the tropospheric jet, which is expressed as a negative phase of the southern annular mode, SAM, at the surface in the pressure field in our mid-spring and summer seasons. This stratosphere-driven negative SAM is an important forcing for prolonged hot and dry, and therefore bushfire-conducive weather conditions in Eastern Australia, like what happened in late spring 2019. So this dynamical chain of processes from winter to summer, from the top of the stratosphere to the surface, is an important source of predictability of spring polar vortex and subsequent SAM and associated Southern Hemisphere regional climate anomalies. So getting these dynamical processes right in dynamical models is critical for skillful seasonal forecasts of the spring to summer climate anomalies and reliable projections for the future climate of the Southern Hemisphere. In this study, we focused on this latter topic by evaluating CMIP6 models for simulating this dynamical evolution and trying to understand its implication for future projections of the polar vortex and associated SAM for the end of the 21st century. So for this study, we analyzed the 43 CMIP6 models with their first available members with the historical forcing for 1979 to 2014 and the SSP5 8.5 forcing for 2075 to 2100 to capture a clear signal from increasing greenhouse gases, although this highest emission scenario is unlikely to be eventualized. For the observation analysis, we used ERA5 reanalysis data. Then, our first question is, how the models simulate the relationship between the meridional shifts of the winter stratospheric jet and spring polar vortex anomalies, which is conveniently captured by this anti-correlation between the winter vortex winds at 1 hectopascal level and subsequent spring vortex winds at 10 hectopascal level, both at 60 degrees south. The era 5 correlation is negative 0.5. In contrast, the majority of the CMIP6 models simulate positive correlations, and only 5 models get the observed anti-correlation right, although these models' anti-correlation strengths are significantly weaker than the observed. For convenience, we will call these 5 skillful models blue models, and the other models red models. Here you would wonder where ACCESS-CM2 and ESM 1.5 perform for this stratospheric process. So here they are in the red model group. Although the ESM 1.5 is less erroneous than CM2 for this particular measure. Then our next question is, what could be the source of the model errors in simulating the winter to spring vortex evolution? To address that question, we looked at the climatological jet position at 1 hectopascal level, where we observed the winter stratospheric jet sits. In this graph, the thick black line shows the ER 5, the dashed black line shows the all model mean, the thick red line shows the red model mean, and the thick blue line shows the blue model mean, and thin lines show the individual models. Here you would notice that many models actually have significant biases in the winter jet location to be around Antarctica, not in the mid-latitudes. The all model mean shows about 10 to 15 degree poleward biases in May, June, and July, largely due to these red models. Interestingly, the blue models that simulate the anti-correlation between the winter and spring vortex winds are actually the good models that correctly simulate the winter jet location. Indeed, there is statistically significant relationship between the winter stratospheric jet position biases and the errors in the winter to spring vortex evolution. That is, the more the model's winter jet, the stronger the erroneous positive correlation between the winter and spring vortex winds. And the ACCESS models that are red models do have these forward biases of the winter stratospheric jet. Then our final question is, does a model's ability to accurately simulate the correct location of the winter stratospheric jet and the associated dynamical evolution of the vortex anomalies actually matter for future projections of the polar vortex and surface SAM changes? Our short answer is yes. By the end of 21st century, under the highest greenhouse gas emission scenario, all model mean project a strengthening of the southern hemisphere winter stratospheric jet in the upper stratosphere and an equatorial shift of the jet in the mid to lower stratosphere. And these stratospheric vortex changes coincide with the strengthening of the tropospheric mid-latitude jet. And the SAM is projected to be more positive. And these spring changes are also found in these winter changes are also found in spring. In comparison, the blue model mean projects a clear poleward shift of the winter stratospheric jet that would act to weaken the spring polar vortex, according to our understanding discussed here so far. Interestingly, the spring zonal wind change is significantly weaker in this blue model mean than that of the all model mean, which is likely due to some cancellation between the radiation-driven strengthening of the vortex and this dynamics-driven weakening of the vortex. Because the spring polar vortex change is only moderate in the blue model mean, its positive SAM projection is also weaker than that in the all model mean in spring season. So to conclude, our model evaluation results point to another source of uncertainty in the all model mean projections for the southern hemisphere climate in spring and likely in summer as well, when the stratospheric polar vortex changes significantly impact the SAM and associated Southern Hemisphere regional climate changes. Good news is that there are some studies that have reported some improvements in the Southern Hemisphere stratospheric circulation and temperature simulations by improving gravity wave parameterizations. So hopefully we will have some more number of blue models in the CMIP7 ensemble. So that's all. Thank you for your attention.
Notice that having more model levels, vertical levels in CM2 didn't help, so no.
Yeah, but in our investigation, the results weren't quite sensitive to the vertical resolution. Yeah.
So this seems like a really good candidate for a metric to be testing new models with, right? It's quite simple.
Yeah, yeah, certainly. And this polar vortex variability is closely related to the wave activities from the troposphere. So even if we don't directly improve, like gravity wave parameterization, by improving other aspects of the tropospheric features, maybe we will see some improvements. So yeah, it'll be interesting to see.
I'm not sure whether you just mentioned that, but did stratospheric resolution, did the models separate on stratospheric resolution, the ones that did well? Or?
So it was not particularly obvious that like improving the, for example, vertical resolution, like high-top models perform better. And I think those five skillful models, like one is Japanese MEROC-6 and the other group is actually ESM models. And I think, like for example, for MEROC, they put a lot of effort to improve this kind of gravity wave parameterization. So, yeah. So at this stage, I'm not quite sure, whether like improving the resolution was kind of directly impacting the performance.
It would be interesting to run it through the ESM 1.5 large ensemble to see whether it varied much across the ensemble.
Yeah, and it's interesting that like ESM 1.5 performs slightly better than CM2. So, yeah.
All right, we better,
Can I just ask a question? Can you remind me whether that CM2 submitted there for CMIP6 had interactive ozone chemistry?
As far as I understand, I don't think so.
Yeah.
no, so it certainly wasn't running chemistry, no.